So good morning, everyone, and thanks for this very nice invitation. Today I'm going to talk about a methodology called Gaussianization that allows us to cope with the particular statistical properties or characteristics of the Earth data. And I will show you how it works, how easy it is actually, and also a good bunch of Earth applications, from data synthesis to anomaly detection, as well as information theoretic measure estimation in both space and time and altogether spatial temporal dimensions. Basically, my main intention in this talk is to convince you about this wide applicability of Gaussianization in general, but for the earth sciences in particular. Okay, I guess that you can see this very nice animation of the Earth, or rather a simplified view of what the Earth is. So this way, in this way with the Earth is basically a nice mathematical object defined in a multidimensional space. And this object can be characterized in many different ways with many different quantities of interest. And we basically observe this object with satellite sensors and try to understand with model simulations as well at a certain spatial temporal spectral resolution. And you see here that there are like a few essential climate variables that I plotted, but you can see that there is a lot of strong spatial and temporal autocorrelation of the signal. You can see that the evolution across time is very remarkable. There are also some strong seasonal cycles, and they are all correlated across space and also across different variables too. So all in all, it's a very complicated object that we are interested in. And we could say that statistically, basically, this object is a multidimensional, complex, nonlinear, non-Gaussian, strongly autocorrelated in space and time, and overall, it is also multi-source. So now the question is how to study this object and the interrelationships that we are readily observing. Well, my point in this presentation is that the characterization and analysis of such complex objects can be done, or should be done through the estimation of multivariate densities. And then, I know your answer. Okay, yes, of course. But we all know that estimating densities in high-dimensional spaces is very hard, if not impossible. With just like 5 to 10 dimensions, one needs millions and millions of data points for a naive histogram-based estimation. But why do we want to resolve that complex problem instead of more simpler tasks like classification or regression problems? Well, the point is that this question is not incidental. I mean, the PDF estimation problem is at the core of almost every statistical, machine learning, and information theoretic estimate. In almost all information theoretic quantities like entropy, mutual information, or Kullback like versions, etc., you have a probability to estimate. But these are very hard to estimate, and one resorts to approximate methods like nearest neighbors or basically adopting the standard Gaussian assumption. And very often one just estimates univariate measures. That's the second part of the story. In machine learning, we have typically preferred to estimate decision boundaries instead of densities for doing classification, for instance, trying to resolve a much simpler problem. And even in Bayesian inference, one prefers to simplify the estimation problem with the smart sampling schemes, not the real tough one. No? Okay. So the key point in Gaussianization is depicted here in this plot. We want to transform this arbitrary multivariate density into a joint Gaussian. This has many advantages, yet the most important one is to estimate densities and also information theoretic measures, as you will see in a minute. To resolve this problem of Gaussianization, one could think of going dimension by dimension, for instance, and marginally Gaussianize. This is very simple. You only have to uniformize each variable based on its CDF, and then apply the inverse of the CDF of a Gaussian, and you're done. So this is quite simple, right? But this is actually wrong, or not actually what we are looking for, because marginal Gaussianization does not achieve this multivariate Gaussian. Only the two features are Gaussian, but not the joint distribution as we wish. No? Okay, so the method that you will see in a second allows us to estimate multidimensional densities, just in the same way that we typically do meatballs. So you first squeeze marginally each dimension and then rotate. And then you repeat this process several times. And this is it. So, well, okay, more formally, one has to apply these two transformations, right? The marginal Gaussianization psi here in the formula and a rotation R on the data at each iteration K. So this will be an iterative procedure. One basically can demonstrate that this transformation is invertible, differentiable, is valid for any orthogonal transformation, a rotation. It converges in mutual information and entropy to a Gaussian, and it is quite fast and has also, as we will discover through this talk, a very tight connection to neural networks and also information theoretic concepts. Well, the transformation leading the data to a Gaussian is, however, not the relevant thing here. I want to stress this. We are only interested in the inverse of this transformation, since it allows us to estimate a PDF in the input domain. Going to a Gaussian is basically because of convenience, because it allows us to come back. Okay. So for doing this, let's say, invertibility trick, we only rely on the standard change of variable formula. So the P of X is essentially the P of G of X times the determinant of the Jacobian of the transformation. Now the point is, do we actually know these two terms? Well, the point is that these two things are known, essentially because we know that we end up in a Gaussian domain, so we know the formula for multivariate Gaussian, plus we can compute the Jacobian of the whole transformation as the multiplication of the Jacobians of each step. And of course, it is invertible since the inverse of the rotation is just the transpose, and the marginal Gaussianization is also trivially invertible too, right? So yes, one can also demonstrate that this converges in two different senses. It converges in mutual information to 0. I mean, in the end, you will get mutual information 0 or total correlation 0, and also in Kullback-Leibler divergence to a multivariate Gaussian. I'm not going to enter into the details of the demonstrations. Everything's in the papers. Well, this is the same thing for mutual information demonstration. And look, it works. Here we generated this kind of funky 2D example where we put a lot of mass in one particular legs of this distribution. And after several iterations, the distribution is transformed into a 2D Gaussian. In this particular case, it takes like 20 or so iterations only. And we also try it with images of different nature, natural photographic images, radar images, multispectral images as well. And here we just took pairs of neighboring pixels. So still we are in a very simplistic 2D setting basically for visualization purposes. And RBIG, this is the name of this Gaussianization technique, the rotation-based iterative Gaussianization, RBIG for short, basically returns like better results than a competing method called radial Gaussianization technique, which was especially designed for natural images. And the good thing is that you can really see in the last column that the joint is a Gaussian and the mutual information is virtually 0. But there is more. Remember that RBIG allows you to go back and forth between the arbitrary input domain and a Gaussian domain. And then sampling from a Gaussian domain is really trivial. So we can invert back and generate synthetic samples. Here we can, for instance, convert these rings to spirals and vice versa by basically concatenating two RBIG transformation. One I'll learn from rings and the other the Gaussianization transformation from this crosses. And then we can sample from a Gaussian domain and use the inverse of the transformation of the other to transform a ring on a star or whatever. And since again sampling is really free, we can train a Gaussianization transformation for a big data set of faces, for instance. So we learn how to Gaussianize faces and then sample from a multivariate Gaussian and invert back to the samples. On the top row, you have the real faces, and in the bottom row, you have the RBIG generated faces. And it is pretty hard to differentiate among them, especially some particular cases that they are astonishingly good. Okay, but now let's move on now to more interesting problems in earth sciences. In this particular problem, we wanted to estimate carbon fluxes from satellite data and in situ measurements from these FluxNet network. You can see here the sampling, and the sampling is pretty, I mean, the location of the different flux towers, and it is heavily imbalanced, at least spatially. These flux towers allow us to estimate many different variables, like exchange of carbon dioxide or maybe, yeah, as well, ecosystem energy, ecosystem exchange, energy budgets, etc. And then what we did is basically collocate Moody's sensor observations with the flux tower, sorry, estimates, and then we run a regression method, either a linear regression or a Gaussian process regression, in order to predict the carbon fluxes now in space and in time, every time we have a satellite acquisition. So I'm showing you here the scatter plot of the training data. So you can readily see that there are some variables, some input variables that are quite interlinked, quite dense in these scatter plots. But there are some others that they show like a very sparse and discrete scatter plot. In order to compensate for these missing points and missing relationship, we use RBIC to populate the space. So we took this data set, learned how to Gaussianize it, and then from this 10,000 point, we generated 1 million points, synthetic points. We put everything together, and then we train a linear and a Gaussian process regression. And yes, apparently the real plus synthetic data was a kind of a richer and more useful for prediction. And actually, you can see that in all quality measures, the mean error, RMC, the mean absolute error, the Pearson correlation coefficient, everything is improved, especially when you're using Gaussian processes that benefit quite a lot of this joint Gaussian assumption. Okay, so now we have seen examples with, let's say, small to moderate dimensionality problems. But what happens if we go in much higher dimensions? Instead of just 10 dimensions, here we want to generate synthetic hyperspectral pixels from Aviris, which is a sensor that basically acquires images in 224 bands or dimensions. And we used RBIC for this. We use this Gaussianization technique for this. So you can see on the bottom left that the mean spectra that it is generated, it resembles quite well the original one. But one has to look at the joint relationships. In the middle, we show here the real joint distributions, but only for 4 spectral channels of interest, 4 dimensions. While on the right-hand side, you see that the synthetically generated samples, they mimic quite well the distribution of the original one. The RBIC captures higher order representations very nicely and allows us to generate like realistic pixels. What is this useful for? Well, we typically use it for robustness test of whatever regression or classification algorithm that we are applying to the scene, or for running emulations, and to check if the emulator is robust to similar but not exactly the same distribution examples, etc. But there are other applications. An interesting application is that, a standard application actually of density estimation is that of anomaly detection. So intuitively, we just use the inverse of the probability as the score of anomalousness, let's say. So the RX method on the top is basically based on the Mahalanobis distance, and the main assumption here does not hold in this particular example. The data is basically non-Gaussian, so that's why it shows very, very poor performance. On the other hand, in the middle, you see the resolution of the anomalies detected by the kernel RX, a nonlinear version of the standard RX. And it is better than RX, but some false detections emerge in the outer circle, especially on the bottom left. On the bottom right. Mainly, this is basically related. We hypothesize related to the critical issue of tuning parameters in kernel methods, in particular in this kernel RX. And on the right-hand side, you can see the solution of RBIG, and the direct application of RBIG easily identifies the anomalous points, since basically they are far from the most, from the more dense and also more probable region. And it's doing quite a good job in here in this example. But we apply it to many different anomaly detection problems involving droughts, floods, fires, etc. And in all cases, the RBIG method outperform, well, in some cases by a lot, some others, but not that much, but always kind of generalize and improve the results of standard methods for anomaly and extreme detection. With an additional advantage that you should know that this method is parameter free. You don't have any parameter to tune actually, other than the number of iterations that you want to, or number of layers or iterations that you want to tune here, but it is not like a dramatic parameter to tune in the end. Okay, so far so good. But there are more interesting things about this method, I should say. Remember that in every iteration, we were reducing the mutual information towards zero. This is a classical measure of dependency between random variables in the end. But actually, RBIG can be used to estimate mutual information, but many other quantities as well, information theoretic measures. So first, let's talk about a little bit about the total correlation, also known as the multi-information. It's just basically resource to compute only the sum of the reduction in mutual information through all the iterations, right? Because you are ending in zero mutual information. And this boils down to compute only the sum over all the marginal entropies. This is univariate, this is trivial to compute, and there are many good, very good estimators over there. So you can actually compute the total correlation with this formula. The second measure that we are typically interested in is the multidimensional entropy, and this again can be put as a function of the total correlation as well, minus the sum of the marginal entropy. So all in all, the quantity is pretty simple to compute. You already have the TC because you have been training your Gaussianization technique, and then you have your model. Then you can accumulate all the marginal reductions in entropy, and then you compute the TC, and then you have also the sum of all the marginal entropies. So this is simple as well. The third, sometimes we are concerned about comparing two distributions. So we can do this with this method, RBIG. The KLD divergence between P of X and P of Y, and for this we basically need to estimate the non-Gaussianity, which is defined as the divergence of a particular distribution with regard to another distribution, to a Gaussian distribution. This can be very easily calculated by basically evaluating your TC, your total correlation of the transformed data Y, let's say, through the Gaussianization transformation of X. So you learn a Gaussianization transformation for X. Then if you transform X, of course, it is a Gaussian, and then you apply this transformation to Y, and then compute the total correlation as an estimator of Kullback-Leibler divergence. And the fourth one, yes, you can also use or reuse the previous quantities, the TCs in particular, and reuse the standard definition of entropies to compute conditional independence. And we can use this TC to estimate the conditional independence between X and Y given Z. But how do we estimate this total correlation in the end? Well, in practice, it is very, very simple. We know that we end up in a multivariate Gaussian after enough iterations. So the TC or mutual information is zero. And then we only need to compute how much mutual information is reduced in each iteration. And this is pretty easy, because all the transformations that are involved in this method are either marginal, the marginal Gaussianization in every step, or a rotation. So you can actually compute the reduction in every iteration very, very easily. Okay, and in order to check the estimation results, we did a lot of validation with PDFs that for which we have ground truth, basically three standard PDFs. So the Gaussian distribution with zero mean random covariance matrices, linear transform uniform distribution, and a multivariate student distribution with different degrees of freedom that basically controls the weight of the heaviness of the tails, the weight of the tails. So results in general show that while some methods behave well only in some particular distributions, you can see here that they are highlighted in light gray, RBig is consistent and always obtains a good performance for all distributions. Well, always except for one case. Only when the distribution is Gaussian, RBig is outperformed by the XF method, which basically assumes a Gaussian distribution. So you are assuming the right, you are making the right assumption. So that's why it is outperforming RBig. But in general, being a non-parametric model, this RBig methodology will generally provide more sensible estimates, especially in real scenarios where you don't have you don't have access, or you cannot assume anything about the degenerating mechanism. And I think this is pretty important. And actually, the effect that you see here in the total correlation on the table on the left, you can also see this in other quantities that we estimated, like entropy or Kuba live divergence in no ground truth data. Okay, I would like just briefly talk about this application of RBig for evaluating neural networks. In the end, RBig can be seen as actually a neural network in which you have different layers and you do marginal operations, which are squeezing functions very similar to a sigmoid kind of. Plus a rotation, which could play the role of the weight matrix in every layer. But here we are using RBig for estimating the quality and how the learning process is done by different neural networks. Essentially, what we did here is we were interested in training a neural network to estimate atmospheric temperature profiles from a particular infrared sender, IASI. This IASI sensor so originally 8,000 plus spectral channels, and we want to estimate from that the different temperature levels at the different different temperature values of different layers in the atmosphere. And in this particular case, we run this three-layer network, and we were able to estimate quite accurately the temperature levels. But the interesting part here is how can we use the mutual information, let's say, derived from RBig, to estimate how the network is learning. So what we did here is, for instance, in bottom left, we show how the mutual information between the predicted and the actual output evolves consistently within mean square error for the training and the test set. This is nothing new. I mean, both quantities are related. But the important thing, I think, is the figure bottom right, where we show the evolution of the mutual information between the output layer of each layer and the output of the training data of the neural network. So we are comparing multivariate data here. Something that it is not really possible with MSE or MAE, for example. In this example, we can see how the last layer, for instance, the layer 3, learns very fast at the very beginning. And at some point, the learning rate drops, and it keeps learning, but very slowly. On the other hand, you can see here the curve of the L1, that it starts to learn kind of slowly, and it keeps learning at a medium rate for a longer time. And at some point, it saturates, and it seems to stop learning. So that would be a good measure to not only to monitor training, but also to apply pruning techniques if you don't want to overgrow the network, for instance. Now we have a very reliable tool to estimate total correlation of multivariate objects, like this very high spatial resolution imagery here. Here, in this case, we have 20 classes and only 100 images per class. We sampled the images in patches, and we created this multidimensional data set. So in this case, RB converges very fast. Note that this is the figure on the bottom middle. There is like this logarithmic scale on the total correlation convergence. So it is very fast in convergence. So basically you need like something like 20 to 30 iterations as a most. And then what you can do is to estimate this total correlation per class. And then rank let's say the complexity of the class of images. We generated this bar chart on the bottom right. So essentially you can see here that more texture classes like runways, freeways, or maybe buildings as well, they lead to higher TC, to higher total correlation, while rather, let's say, homogeneous or flat classes like chaparral or agricultural or forest, they reveal like low information content or not that much complexity. Okay, and what happens if we want to scrutinize spatial, not only spatial but temporal data? So here we were interested in drought detection. In this experiment, we wanted to quantify the information in and between different variables that are typically used in this arena, like land surface temperature, the vegetation index NDVI, soil moisture, and a recent one called vegetation optical depth that accounts for water content in the plants. And we wanted to study this for a particular study area in California. We show here time series of normalized VOD, NDVI, soil moisture, LST, and we also show here on the bottom the SMADI index, which is a very well known and widely used index for detecting the severity of a drought. So what we did is essentially to estimate. First, we wanted to compare the entropy for the different variables. How much information do they convey, and what's the ranking among them? And on the bottom figure, we compared the contribution in entropy of an extra one, the VOD. This variable has never been used before for this particular applications, and we were very interested in, okay, append this VOD to the standard SMADI index, and let's see if we can improve the detection or not. Okay, on the one hand, the amount of entropy for VOD is like the highest in all temporal settings. On the x-axis, you have the entropy for different temporal settings, different lengths, and it is kind of closely followed by LST, by temperature. All variables like decrease in entropy as we add more and more temporal features, and NDVI like saturates around 1.5 bits, something like that, where the other variables have like a steady smooth decline. We can also see that LST and VOD show like the largest difference actually between drought and non-drought periods or years, and that the difference is the largest as we increase the temporal dimension. This is pretty a very nice conclusion of this work, because that really suggests that LST and VOD observed during longer periods could be more insightful, more useful for detecting droughts. And finally, I would like just to go to the combined action, right? Because we were talking about the spatial temporal relationships, and this is the final experiment that we have run. And in particular, we have used this Earth System Data Cube, that it is a good bunch of variables, of essential climate variables, harmonized in a very nice grid over a decade of years, and yeah, a very nice temporal resolution. So we could actually quantify in space and time, and the trade-off between space and time, the information conveyed by different variables and all together. So essentially, we took cubes and estimated information content and different spatial temporal granularity from all spatial on the left, like this 7 by 7, to all temporal, 46 times 1 on the right. So you can basically run sample first, like mini cubes out of this big cube, and then estimate information quantities. And you can plot that in these very nice plots. Here we indicate the entropy, for instance, for two particular variables of interest, precipitation on the right, on the left, and sensible heat on the right, between the, let's say, the fully spatial, ratio 0, and the fully temporal representation, ratio 1. Well, you can really see that trends are very clear. And in particular for precipitation, there is like almost a linear trend here where incorporating temporal information for any amount of dimensions has like higher expected information. While for the sensible heat, the entropy path is, well, is similar, but at the same time, it reveals like a fast increase in entropy for particular configurations of the space and time relationship, something like around 0.8 trade-off, you start increasing the information, right, quite a lot. So the results suggest that every single variable has to be treated differently, and also it gives you like a quantitative manner to exploit the information content of the different variables. Of course, you can come up with very nice maps where the information is dominating, either the spatial or the temporal. And I'm not going to take too much attention to this slide for the sake of time. And basically, I would like to end up with some take-home messages. Essentially, there's one. RBig is a fast method. It's unsupervised. It's kind of useful for and quite robust tool for PDF and information theoretic measures estimation. And I would like you to, I mean, I would like to use it. I would like to recommend it to you. It is available in Python and MATLAB. And just a few words about our future steps. We are very interested in trying to learn the whole transformation in one shot, not iteratively. Also, we want to use it for conditional independence tests. We have the equations, but we didn't find the time. And also for conditional density estimation too, which is also possible. Yeah, and here you have some references about RBig, the original paper 10 years ago. Yes, RBig is now 10 years old. And I would say that as a regular teenager, it is becoming mature and rebel and wants to explore more and more adventures on Earth. So thank you very much.
Thank you very much. Very interesting methodology and applications. So there's questions maybe from the audience in the KITP room and of course online. If you want to ask the question online, please raise your hand in Zoom so I can see it. Is there anyone first from the audience in the room who has a question? I don't hear any. Yeah, okay. Yeah.
Hello. I had a question about your slide talking about how quickly different layers learn information in neural networks. So in there, you mentioned that you found the latter layer in the network to converge fastest. I was wondering if you're familiar with like spectral bias theory, where we have like an understanding that neural networks learn large scales faster than small scales, which I think in some cases has been found to show that the large scales are learned early on in shallow layers. And if you have any sense of kind of the scales of information being learned in the network when you have the latter layer converging fastest.
Thanks for the question. The main motivation of this particular application was from the theory of the bottleneck, information bottleneck in our networks. So we are actually not working with images here. So I guess that when you're talking about scales, you're talking about different spatial scales, right? Or is it a different scale that you're talking about? Or?
I mean, scales can be, I guess, somewhat abstract. I know, like time series or images.
Okay, yeah. No, I'm not really aware of this spectrum theory that you were mentioning. But in principle, the technique could be actually used for analyzing this sort of networks and maybe nice comparison to these methodologies. What we have observed is that basically some of the works that have appeared, they have been kind of controversial in the literature concerning this information bottleneck. have paid the price of estimating information marginally. I mean, you can of course do it, but you have to go like neuron by neuron in a particular layer, and then sum everything up, or just to compute the average or something like that, and a kind of an heuristic to summarize everything. And in here, as a big difference is that we can do that with multivariate data, and the difference is quite noticeable actually when you apply it to arbitrary neural networks. Yes.
Thank you.
Thank you very much. Any other question from the audience?
Yeah, I had one.
Yeah.
If you don't mind. Yeah, I will.
Go ahead.
Hi, Gustav. So Mike is Zonneveld. I think we met last week or the week before. I was wondering if, I guess I have two questions. One, in your first validation slide or demonstration slide where you had the circle and then also the sort of wiggly X, I noticed that there were some sort of systematic dots around the outside, and I was just wondering if you could speak to that a little bit. I probably just missed something. And the other thing was that all your examples, they don't, at least as far as I could tell, account for uncertainty. So, we have different data points, but especially, in observations, largely, especially if you're comparing different data sets or different dimensions, they'll have different sort of uncertainty bounds associated with the individual value. Yeah, that's the slide. And I was wondering if you could speak to that as a little bit as well, in terms of turning those types of distributions that are, very high dimensional, of course, but also have the added layer of complexity of uncertainty associated with them, with your methods.
Yep. Yes. Very, very nice questions, actually. The first one, yes, you are completely right. The first point, I think this is the slide that you were talking about. Right?
Yeah, correct.
So, well, the first point is that as soon as you have just a Gaussianization transformation, the transformation is invertible. So you can go from the circle to the Gaussian and the Gaussian to the circle. There's no particular error in there, other than numerical errors of the implementation. Right? The problem here comes when you are sticking together two different transformations, and one is and also about the big differences and maybe the small errors that you can readily notice here on the corners, right, of the circle here and here.
Could you a little bit closer to your microphone?
Sorry. Yep.
Sorry, maybe it's just me.
That better now? Yep.
Yeah, no, that's great.
Okay, sorry. Yeah, so in this particular cases are basically due to the fact that you're doing the inverse of a transformation and applying it to another transformation itself. So there are like carryover, let's say, effects or imputation of errors in there. Of course, you can. I mean, at least in these particular cases, we couldn't get rid of those errors. It is just an example for fun, of course, but you are completely right. This is a caveat, right? When you are sticking Gaussianization transformations. That's right. And the second question was about uncertainty, right?
Yeah.
Yes. Actually, this is very related to this point. I mean, as soon as you have variance in the input domain, and you are learning through that, that translates into the Gaussianization estimation, because you are going forward and then backward in the inverse. So there is actually a related field nowadays in machine learning called normalizing flows, and this is actually an instantiation of a normalizing flow, and they are very promising in nature, but essentially you will be facing like very similar problems to those that you have in neural networks, like exploiting gradients. Here, instead of exploiting gradients, you would have exploiting inverses, right? Because remember, we are not really particularly interested in the Gaussian domain in the end, but inverted them back. So the problem here boils down to have good estimates of the Jacobian and the determinant of the Jacobian. So every error that you commit in there, that may turn into a dramatic error in the estimation of the PDF, of course. Yes. Yeah, but completely agree. I mean, more analysis has to be done in the propagation of errors. Certainly. Yep.
Yeah, I'm nodding, but you can't see me, of course.
Yeah, thank you very much. Any other questions from the audience? Still have time for one question. If not, anyone online? I see no. No, maybe if you go to the one by last slide where you have this map, right, on the information content for precipitation and sensible heat. So what meaning can you attribute to that in terms of, you know, the physics behind it?
Yes. Wait a second. This is going very, very slow. Yes,
Yeah.
You mean?
Yeah, you're nearly there.
Almost there.
Yeah, next one.
There is one. Okay, perfect. Yes. So here what we are plotting is the trade-off. It is a divergent map. We are plotting the trade-off between spatial, fully spatial, or temporal, who is dominating more the information in precipitation and sensible heat, right? Mm-hmm. So in regions where we expect like pronounced seasonal patterns, the information or the complexity, if you want, is apparently high in fully temporal configurations, because essentially the seasonal cycle controls the ecosystem dynamics, and that's a fact. Actually, in seasonal, let's say, temporal modes are of lower informative content in the spatial domain, as they are mainly driven by solar forcing, especially in sensible heat. Then the information values tend to be higher in tropical regions, right? Whereas arid regions show like low complexity, low information patterns. But looking at the precipitation, for example, on the left, spatial information dominates in desertic areas, like you can see here in Australia, in Iberian Peninsula, in Sahara, in Mexico, which are reasonably independent of time. And the temporal information dominates in Sahel, savannas. So northern latitudes as well, maybe also in southwest China, which are generally characterized by high rain factors, seasons, and moisture overall. So you can actually start interpreting these patterns of domination of the spatial or temporal, and that gives you kind of some hints on how to manage in order to develop your particular models of estimation, prediction, or just anomaly detection, because in the end everything's actually related.
Oh, yeah. So you could see the monsoons from there.
Yeah, kind of. Yes, in the sensible heat, actually, this is one of the patterns that pops up quite clearly.
Yeah. Okay. Yeah. Thanks very much.
Welcome.
Okay. Thanks again, Gus, for the nice talk and answering the questions. And then we go to the next speaker,